Hey everyone, welcome to the videos for Gear 1. There are actually two videos for Gear 1, and it'll be the same thing for the other Gear projects. So the first one's always going to cover the SAS programming portion, right, showing you what you need to do and so on and so forth, what variables you need to set up or what types of variables you need to set up. And then the second video will show you how to set up your slides to present your study, all right, to present your project. Okay, so you don't have to worry about making an actual presentation and things like this. This is the slide presentation is just kind of a chance to show you how you would set up your slides for an actual study. All right. So some of you, especially in psychology, puts a lot of emphasis on students doing presentations, research presentations. But others of you might also have chances to present at maybe a conference, a professional conference, presenting your research there. And the gear projects are designed to kind of help you understand what your project slides need to look like in order to present them to a professional audience. Okay. All right, let's go ahead and get started. Okay, so for the overview of the project, as I have here, I want you to think about a real world phenomena. Okay, so in the slides that are upcoming, you'll see that I focus on crime rates. Okay, and what I want you to do is, I want you to think about what that phenomenon looks like in terms of a distribution. Okay, just in terms of a distribution, and again, you'll see what I'm doing with crime rates in this video and then also in the next. All right, but I want you to imagine what that phenomenon would look like. Again, in terms of a distribution, like we've been studying, like you saw in chapter 2 and then again in chapter 5, what that phenomenon would look like under 4 different conditions. Okay, and I want you to think in terms of moments that we covered in chapter 5. So the mean, the standard deviation, skewness, and kurtosis. Okay. All right. Now, since I'm asking you to do something kind of different, right? It would be best for you to think of something that you understand pretty well, that you know pretty well, that you've heard a lot about. Okay, and something that you could measure across individuals, or as I talk about in this video, looking at crime rates in across cities, looking at crime rates across counties. Okay, let's say if you were looking at I don't know, SAT scores. Okay, so how would SAT scores be distributed? What would that distribution look like among a group of students from very wealthy families? What would it look like among groups of students from uh, you know from poor school districts? Okay, like maybe the types of school districts or the types of poverty you find in school districts in rural areas. Okay, all right, but you want to think about that thing, okay, that phenomenon, and you want to think about it in terms of a distribution. All right, and then what you want to do is imagine what that distribution looks like in 4 different conditions. Okay, all right. Now what I'm asking you to do is sort of easy, but it's not. Okay, um, because typically you haven't had a lot of chances to do this type of thinking in your education. All right, but here we're trying to kind of push you up to uh, thinking, being able to think more abstractly about distributions. Okay, all right, because this is the type of thinking you're going to have to do in your upper level classes in statistical analysis, research methods, and the like. Okay, all right, you're going to be asked to think about a problem and then imagine what it looks like statistically, quantitatively. Okay, all right, so we're going to try to give you a taste of that here. Okay, so what we're going to do once you have that once you have that phenomenon in your mind, and once you have the distributions for the four conditions in your mind, what I want you to do then is go into SAS and then create those distributions. Okay. All right. And so the function we're going to be using in SAS, if you look at the last bullet point down there, the function I'm going to suggest that you use. You can use any of them, but the random number function I strongly suggest would be the beta function. All right. So in the examples that you see in some of the upcoming slides, you'll see me using the beta function, and then I'll also show you how to set up the beta function in your SAS program. You've done it several times already with your lab projects. Okay, not the beta function, but other random number functions. Okay. Okay. The two rather significant sections of the project are these. Okay, so analysis of the distributions, and then reporting the results of the analysis. All right. So in the analysis of the distributions, you want to use, once you have your distribution set up, you want to simply do like a proc mean statement, and you want that proc mean statement to generate, at the very least, you can add more, but at the very least, you want it to generate a mean, a standard deviation, a skewness value, and kurtosis for each distribution. Okay. All right. And so that's pretty simple. You've actually done very similar things for your lab projects. Okay. The second part of the analysis is constructing a graph. And again, you've already done this many times. Well, not many times, but several times. And so I'm asking you to do the same thing here. Construct a graph of the distribution. You'll see in mine that I just generate some histograms. But again, there are other ways to show it. So, have at it. You can do histograms like, what I show, or, come up with a different way. Okay. I always encourage you to try something different. Okay. Unless it's drugs. Okay. Then stay away from that. Okay. For the reporting the results, all right, you want to make sure you include a graph of each distribution. So you're going to have 4 graphs in there. Okay. And then you're also going to make sure you have some method of showing me what the numerical values of the moments are for each distribution. Okay. And so when you see in the slides, in the following slides, I put all the information about the moments inside the graph. Okay. All right. So I'm not there's more that we could actually put into the report, reporting the results section, right? But that's all I'm asking you to do for this first gear project. All right. In subsequent gear projects, we're going to add a little bit more information, a little more discussion to what's happening in the results. Okay. But right now, we're just going to kind of keep it simple and straightforward. All right. And like that last bullet point says, the second guidance for formatting your slides will be coming in the next video. All right. All right. So to think about the first part, right? Imagining a phenomenon. All right. So when we think about crime rates, all right. Now again, I'm not thinking about any particular data. Okay. I'm not thinking about any particular source of actual data. I'm just thinking about, well, what do we typically think? When we think about crime rates, right? Uh, what do we typically think about where crime rates are highest, where they're lowest? Okay. All right. So we think about crime rates as they vary across places. So we think larger cities typically have higher crime rates. Smaller cities typically have lower crime rates, right? Okay. So our first two conditions are these. The first condition, crime rates in larger cities. All right. So imagine you have a whole bunch of data on larger cities. Okay. And one piece of data uh, is on crime rates. Okay. So if you think about all those large cities that you're looking at, what do you think the distribution of the crime rate would look like? Okay. All right. All right. And then you want to do the same thing for small cities. Come up with, you know, think about a whole bunch of small cities. All right. So, and then think about, all right, well, what would the crime rate look like in those small cities? Okay. All right. And then the other two economic conditions, or other two conditions rather. Okay. Crime rates vary across um, economic conditions. So impoverished areas, we typically think those have much higher crime rates, right? We typically associate poverty with much higher rates of crime. All right. We typically associate wealth with much lower rates of crime. Okay. All right. So in these four conditions, the distribution of crime rate should look, pretty different, right? Right. Okay. So, the whole point of this Gear 1 project is for you to take that image of, in this case, what crime rates look like. All right. Put that image into a simulation. All right. So using SAS, like you'll see in just a few moments, create that distribution and then take a look at the moments. Okay. All right. So like I said, we're trying to get you to kind of think at a more abstract level about this. All right. All right. So, and again, I'm not going by any particular, study of crime rates across small cities and large cities, poorer counties versus richer counties, right? I'm just thinking about how we typically think about the distribution of crime rates. Okay. So if I were to draw these out, all right, for small cities, right, we might have something that looks like this, where most of these small cities are clustered down at the lower end of the crime rate. Okay? So we have this axis here, and we have the arrow going from left to right. So the low values are down here, the high values are up here. And that's the case for each of these. Okay. All right. So for among small cities, again, if you have a large group of small cities, we would expect most of those small cities to fall down here. All right. We typically think of small towns, small cities, largely free of crime and so on and so forth. All right. But we would expect those small cities to be concentrated down at the lower end of crime rates, right? Now, in large cities, we might expect more of a distribution, right? To find, many more of these large cities in the higher crime rates, right? Um, you know, they wouldn't. We typically wouldn't expect all large cities to be concentrated up here, okay? But we would expect uh, to see many more large cities at the upper end than we see among small cities, right? And if you were to compare these two plots, all right, you would see that we're small cities. We see some small cities at the higher end of crime, but we see many more large cities at the upper ends of the crime rates. Okay? And then the same thing here for poorer counties. All right, and you don't have to use counties. You don't have to use cities. You could use schools or school districts or whatever unit of analysis you choose. Okay, but among poorer counties, we typically think of crime uh, being much more of a problem, right? Right. So we get much more of a distribution of poorer counties across the higher crime rates, whereas richer counties, again, clustered, much more clustered down here at the low. All right. All right. So what you need to remember, folks, is that these tell a story. Okay. These distributions tell a story. Now you have to help the reader understand what that story is. Okay. And so that's what we're going to do. All right. So when we talk about thinking in greater detail about your distributions, there's things that you want to include in that graph. Okay. First of all, you want to tell your reader, well, what is this axis? All right. Well, here we say the axis represents crime rates. Down here, even though we don't have any specific values yet, down here we say, all right, well, these are very low crime rates, right? These are very high crime rates down here. All right. What's on this axis? Well, this represents frequency. Sometimes, SAS, sorry, sometimes SAS will by default give you percent of cases along this y-axis. Okay. So now the person who's reading your graph will understand much more about what's going on. Right? So this line represents, in this case, an increase in frequencies. Right? And then the frequency peaks right about here, and then it starts going down. All right? So towards the low end, we start to see much more of many more small cities, or whatever the unit of analysis is. Right? We see many more small cities here. Okay? And then when it after it peaks, we start to see a dramatic drop. Okay, so whatever is being represented by this line, whatever the unit of analysis is, we know that most of those units fall within the lower ranges of crime rates, but there are some in the very high ranges of crime rates, but just not as many. Okay. Okay, so now once you have your distributions in mind, right? You have them all drawn out. By the way, you don't have to draw them out, but sometimes it's very helpful when you're thinking more abstractly about what these distributions look like. Sometimes it's very helpful for you to just draw it out, okay? And that will help you set up your variables, right? That will help you set up your SAS program. All right. Anyway, all right. So once you have these distributions in mind, all right, you want to go ahead and start writing your SAS program. Okay. All right. So as I have here, one of the easiest functions to use for this project would be the beta function. Okay. All right. And so as an example of one of the SAS statements that I used, I have here crime rate equals rand, and then in parentheses, and then in single quotes, beta, and then 3 and 12. All right. So now let's talk about what those values represent. Okay. So the only thing you're going to be changing or manipulating here is this value and or this one. Okay. Okay. So the basic setup for this is this. All right. So you're going to create a variable name. All right. And again, that variable name could be whatever you want. Okay. Uh, Followed by an equal sign, then rand, then inside of parentheses, beta in single quotes, and then value 1 and value 2. All right. Both of these values are shape parameters. Okay. Now they don't correspond to um, exactly to skewness and kurtosis. Okay. Even though those are shape parameters, but you use these to change the shape of the distribution. All right. And again, I'll show you what some of the effects are of these two values in the next set of slides here. Okay. All right. But just as a general guideline, just take a look down here towards the bottom of the slide. So here, if value 1 and 2 are exactly the same, all right, then you see a symmetric distribution. And at a certain point, if the values are the same, you'll get what looks like a normal distribution. Okay, and again, I'll try to point that out to you. All right, if value 1 is less than value 2, the shape is going to have a positive skew. All right, if value 1 is greater than value 2, the shape is going to be negative. All right, so the tail is going to stretch in the direction of the highest value. Okay, all right, the tail of the distribution is going to pull in the direction of the highest value. Okay, all right, let's see what we get here. All right, so I got 4 examples. Here are the first 2. All right, now again, I should emphasize this, but on the previous slide, the values that you input have to be greater than 0. All right, they cannot be 0 or SAS is going to return a error message. Okay, all right, but they have to be greater than 0. It can be 0.01. Okay, but they just have to be greater than 0. All right, so if we look at the beta distribution where value 1 is set at 1 and value 2 is also set at 1, this is the kind of distribution we get. Something that looks sort of uniform, right? So each value in the distribution, I just have a generic variable name up here, x1, right? Each value in the distribution has essentially the same frequency, okay? Right? Roughly the same frequency across all values. The same percentage, right, across all values. Okay? All right? So in this case, whatever our unit of analysis is, people or things, right? Those people or those things are spread pretty evenly, not perfectly even, but spread pretty evenly across all values. Okay? Right? So in my case, if I was saying if the values here represented crime rates, all right, I would say, well, all small cities are, almost evenly distributed across crime rates. Okay. So in other words, small cities, some small cities, have very low crime, but almost an equal number of cities have high crime rates. Okay, all right. So in the second example here, right? So we have beta distribution values. Value 1 is set at 100. Value 2 is set at 100. And again, you could set it at 1 million, 10 million, 100 million, or whatever, right? Just has to be larger than 0, okay? But at 100, okay, we get more of a normal distribution, okay? So if you think your variable, in one circumstance at least, is going to have a normal distribution, right? Then one of the ways you can create that normal distribution is to have your value set at 100 for the first one, and then the value 2 also set at 100. Okay? All right. And again, folks, you don't have to use the values that I input. Okay? You're welcome to do that, but you don't have to. All right? All right. If you want to create skewed distributions, again, you want to remember that you want to set the higher value in the direction that you want the skew. All right. So if I wanted to set up a distribution with a left skew or negative skew, I want to make my value 1 a lot larger than my value 2. All right. So here I have value 1 set at 100 and then value 2 set at 1. Okay. So I get this pretty hefty skew in the distribution that's pulling off to the left. All right, so it's pulling off into the direction of the highest value that we set. All right. Now, if I wanted to do if I want to create a distribution with a positive skew, I do just the opposite. Right. Value 1 is 1, and value 2 is 100. So again, the skew is pulling off in the direction of the larger value. Okay. So if my larger value is to the right, the distribution pulls off to the right. If it's to the left, the distribution pulls off to the left. Okay? All right? Okay, so the SAS program to set up the data is pretty easy. All right? All right, so here's mine. Data crime, call stream init. Okay, and again, this number could be anything you want it to be. So I arbitrarily chose 4812. All right. Here I'm creating 1,000 observations. You don't have to create that many, or you can create many more. Okay, but to give your distribution some definition a little bit, use at least 100 observations. So go at least do I equal 1 to 100. All right, at least that many. Right, because fewer than that, then your distribution gets a little muddled looking. Right, but the more observations you have, the more definition your distribution will have, and it will just be easier to interpret what's going on. Okay, so then I have my 4 variables. All right, my variables representing each condition. Okay, so prime 1. Okay, this is beta 140. Okay, so you know from here whatever whatever condition is represented here. We'll get to that in just a second, right? Whatever condition is being represented here, the distribution is going to be skewed to the right. Okay, because we have as our first value 1, and our second value is much higher at 40. Okay, so the beta function is going to make the distribution skew to the right. All right. Now, for this last term here, right, where I multiply this value times 100, this is just something to make the crime rates look a little more realistic. Okay. This is not something you have to do. All right. It's not something you have to do. All right. You can leave that off, or you can put it on there. It's totally your choice. Okay, it's going to depend upon what sort of simulation you want to run. Okay, all right. Here, prime 2, right? Again, using the same beta function, right? We have our first value 10 and our second value 50, right? So again, this is going to pull off to the right but it's not going to, the skew will not be as extreme as the skew that you're going to see in crime one, okay? Because these two numbers are closer together, all right? So it's not going to, the skew is going to be to the right, but it won't be as extreme as what we would find in the first one, okay? And then for crime three, again, we don't know what the condition is yet, but I'll tell you in a few minutes. All right. Here we have 25 as our first value. I'm sorry, 15 as our first value, 25 as our second value. All right. So this is going to create something that looks more like a normal distribution. All right. So again, so the closer those values are, the more of a normal distribution it takes on. Okay. All right. For crime four, all right. Again, we have another distribution that's going to pull off to the right. Okay. It's going to be skewed to the right. Okay. And it's going to be, fairly heavier. There's going to be a fairly heavy skewness, okay, to the right, even more so than what we saw up here for crime one. All right. And then I have my labels here, right? Now, if you want to, or, I could have put uh, some more information into the label, but I decided to put it elsewhere. Okay. All right. And you'll see what I mean in just a few moments. All right. Then I have my prop format statement. So I'm going to apply this to each one. So I'm going to say if the crime rate is 0, put the label very low. If the crime rate is up near 1, put very high. Okay. Actually, that should be 100. Okay. All right. So for the proc mean statement, here's where you want to generate the numeric values, or generate the descriptive statistics for your distribution, right? So you want to write a simple proc mean statement and then say mean, standard deviation, kurtosis, skewness there, and then limit the number of decimals that SAS will output for each of these values. Just limit it to 2 or 3, but just keep it a small, keep it at a small number, right? And then here I have my variables listed, crime 1 to crime 4. Okay. Just in case, I don't know if I've shown you this dash option. Okay. But when you want SAS to run an analysis on a series of variables, right? You just want to put the first variable followed by dash, and then the last variable in the series. Now, in the data, the series, the variables have to follow one after another. Okay, all right. But in that series, you want to put the first variable name, dash, and then the last variable name, and SAS will know that you're referring to all the variables in that series. Okay. All right. For the proc SG statements, and they're largely all the same, just different text accordingly. All right. So here I put SG plot data equal crime. And then for my histogram for crime 1, all right, I have some funky colors here. I don't think I've shown you this particular pattern of fill. All right, but this is one type of option you can use. Right? And then for title, I have figure 1, conceptualized distribution of crime rates among smaller cities. All right? Since I have this title, I didn't put more specific information in my variable labels. Okay? Because the person will be able to read this title and know exactly what's being shown. All right? And then for the footnote, and this is something I want you to include in each of your graphs. I want you to make sure you indicate the whether it's a skewed distribution maybe skewed to the right or skewed to the left, whether it's normally distributed or, platykurtic, okay? All right, but make sure you include this information in your footnote. All right, and then for the y-axis label, you want to include a statement like this, just to help the reader understand what's going on. What they're looking at, okay, and how to interpret those bars in the histogram, okay. And then for the inset, you want to give the actual mean, standard deviation, skewness, and kurtosis for the distribution. Okay. All right. And you want to put this into the graph, right? And then for position, this position is going to depend upon what your histogram looks like, right? So you have several different options for positioning. You want to make sure you take a look at those and then make sure you put that inset where you want it to be, right? So it's easy to read. Okay. All right. For crime 2, like I said, much of the same type of information. I have a title, figure 2, conceptualized distribution of crime rates among larger cities, right? Distribution approaches normality, right? Y-axis label, percent of larger cities, n equals 1,000, right? And then for the inset, mean, right? 16.8, 5.03 for the standard deviation, skewness, kurtosis, border position, top right. Okay. Right. Same thing here. Figure 3, conceptualized distribution of crime rates among poor counties. Right. Again, distribution is approaching normality. Right. Inset. Right. And then positioning. Okay. Same thing here. Crime rate. This is for richer counties. Percent of richer counties. Okay. Mean, standard deviation, skewness, kurtosis. Okay. All right. So for the next part, reporting your results, right? Go take a look at the video for setting up your slides. Okay. I think that's it. Yep. Okay. So take a look at that video, and again, folks, what I'm asking you to do is in one way easy, but it might give you a little bit of trouble because again, a lot of people, not just freshmen or sophomores, juniors, seniors coming, in college, but lots of folks have trouble, taking an image in their head and converting it to numbers. Okay, so that's essentially what I'm asking you to do. All right, so let me know if you have questions or issues about setting up your data. I'll be more than happy to help you out. All right. See you in the next video.